Today we're going to introduce several deep learning models we developed for modeling reasoning in natural language. I guess everyone knows that deep learning is very powerful, but still there are many very challenging problems in NLP, and in general for AI, there's many challenging problems here. There's many people try to view what we can still do to push forward the model for further. So one of these papers published in 2016, I found it very interesting by Lake, who is I think it's a group from MIT. So the published paper discussed some challenges towards building a machine that learns things like people. So they basically think there's still several things that are very challenging. One is compositionality, like we want to enable computer to model the meaning of the whole from the meaning of parts. In language, you can think about like you want to model the meaning of the sentences from the words, but it's not necessarily limited to language. For example, image, you can model the whole meaning of the whole object from the parts. The second problem they found very challenging is reasoning and inference. And the third is like the argue is like intuitive physics or psychology, like also including common sense and also learning to learn. And I myself interested in this paper because I think many of this problem actually existed in natural language processing as well. And even hard, like many of these problems actually entangle with each other. So make the NLP, many of the NLP problems actually quite hard. Today I'm going to talk about the first two, some of our previous work about the first two, compositionality and reasoning. I'm going to focus more on reasoning part, informal reasoning. Means language, reasoning in natural language. But because those problems are entangled with each other, so I'm going to also talk about some of our previous work on compositionality as well. So during the last several years, we performed some research on those two areas. One is modeling informal reasoning and inference in natural language. We actually work on several problems. One is natural language inference. And one of my students, Chen, built a couple models on this. And we also collaborated with Professor Hui Zhang in New York University working on Winograd schema challenges. We also have some paper published on this along this line. The third problem we are working under this umbrella is like recently we're interested in counterfactual modeling. So actually, in this coming year's semi-value evaluation, we're going to organize a competition and shared task for detecting counterfactual in language. I'm going to go to a little more details about this. But again, so in addition to this or related to this, we also work on semantic composition or semantic representation during the last couple of years. So today I'm going to focus more on our work on reasoning and inference, but I'm going to discuss some related work on semantic composition, which is related to modeling the reasoning and inference in natural language. I'm going to start from a very simple example. So if you consider you're going to build a chatbot, and if your chatbot know Tony bought a Mazda 3 yesterday, and he's very excited, and if you ask this chatbot, what does Tony own a Mazda 3? So very likely he's going to not know this. One reason is because even like a simple lexical level inference like entailment, buy means own, or if you push a door, it probably means it's going to open, push open. So those kind of impairment, computer still do not understand very well. So there's a lot of work on lexical level impairment started before, like by Journey and colleagues. If we move to a little more complicated examples, if we have a premise like we know that last year all companies put in Nasdaq saw cost go more than expected even after adjusting the inflation. So if a hypothesis like Google in the book reported cost increase. So if we know the premise is true, then we probably going to also sure the hypothesis is likely to be true. So this kind of problem is defined as a natural language inference problem. Basically, we have two sentences. One is premise, and the second is a hypothesis. We want to find their logical relationship, like whether P entails H, or they contradict to each other, or whether they have no relations. If computer can understand, there's many applications, potential application, for example, fake news detection, right? If you present something which is fake, probably you can find a contradiction as well, right? So this is one problem we are working on in the last few years. It's natural inference problem. I'm going to talk about other problems a little bit, like Winograd a little bit later. So for this kind of problem, we try to build a model to solve the problem earlier or better. So at the beginning, we start to model the lexical level entailment because we think that's a foundation. Like if computer cannot understand entailment among lexicons, it's very hard to understand the entailment or contradiction at a sentence level. So we start to build these type of models from the word level, and also we start to learn, like I said, if you have the building component blocks from words, you need to compose the meaning from words to sentence level. That's semantic composition. Once you get which like Jeff called spot effects in the sentence level, you can do many more things. So we do start this kind of research from the word level. So at the word level, there's some issues about some regular word embedding representation because most of the word embedding actually is based on this slogan saying, okay, you should know a word by the company it keeps. But that also means the models, if you learn the embedding based on this, they cannot tell the difference between like a hypername, entailment, contrasting meaning. Because again, so because those criteria, like you can say, like a word, the word always contrasting meaning, like a love and hate, their contexts are similar to each other. And the word about entailment, their meaning their context can be similar to each other. Also, it's happened for hypernames as well. So again, so we start from building better model at word level. So to build better models at word level. So we do two models. One is like we have a paper published in the coding 2008 is 2018 is about build a model that can encode some hypername information. And also, we also try to build a model to model the contrast meaning. Today, I'm going to only talk about our model to understand the contrast meaning at the word level. Again, you can think about that. This is a word embedding from some embedding space. So you can see like they are going to put much little and more together, and put like a new and old together. So basically, they put the words with a similar meaning or related meaning together, but they cannot tell many other dimension of the difference in many dimension of semantics. So the first work we tried to do years ago is to start from building a model which can tell the difference along different dimensions, which is related to sentiment analysis, related to inference. So one dimension we were very interested is contrasting meaning. So if computer can understand the difference between new and old, love and hate, they can not only do sentiment analysis, they can also tell whether these two sentences are contradicted to each other. For example, well, the first sentence is detached house price in Toronto rose slightly last year. Or second sentence is price of single house decreased almost 10% in the past year in Toronto. So if they know the difference or the difference of the meaning of rose and decrease, they can probably tell that this is contradiction. But again, so that it's not only depend on these two words, it's probably depend on other words as well. But again, the basic things computer need to understand this. If computer cannot understand this, computer cannot tell the difference. So we started to build a model at the word level. So the model we built, like which is published in ACL 2015. It's like we basically like the corpus cannot give us enough signals. We need some training signal to guide the models to learn something along some dimensions, right? So the models the information we want to know, like nowadays probably you can use BERT, and also you probably can use some signal from fine-tuned over there. But in addition to that, you can think about human beings have already built many fantastic existing knowledges over like a dictionary, right? So dictionary already have this information about some dictionary have entailment information, other information dictionaries have already contrasting meaning information. So why not use this to guide the model to learn better representation for the dimension of semantics we want to learn? So basically the model there, from a high level, we want to benefit from the corpus, but we also want to benefit from human knowledge as well. So in that case, the models is going to design a space in which the semantic similar words should be close to each other. Semantic unrelated word is further from each other, and the semantic contrasting words are furthest. So we try to enforce this kind of biases towards the discipline we're going to learn. So again, so the key idea is like we use corpus to learn relatedness, but based on that, because there are different type of relatedness, semantic relatedness. There's similarity, there's entailment, there are contrasting meanings. So we use human knowledge, like you can to guide to constrain the low dimensional space that models can learn. So basically, the idea is like we want to enforce like again. So the distance between unrelated word and similar word. So similar word, the distance of similar word should be closer than unrelated word pairs by a margin of. And the semantically contrasting meaning pairs, the pairs with contrasting meaning should be further than unrelated pairs by another margin beta. So during learning, we try to enforce these constraints to the model, so the model can learn better to represent this meaning. So again, so we test those on standard benchmark data set with GRE contrast meaning data set. And this is some previous models. Again, so if you design those models, carefully, so you can actually just use the large corpus and also the thesaurus, you can actually build a model that actually can build of state of arts before. So there's many other people try to build the models, Microsoft different places. So at that time, so the models, we can say like we start to model this, and if we design the model, design the constraint properly, you can actually learn a very good low-dimensional representations, which it can capture not only similar meanings but also contrasting meanings. So I'm starting from this example by saying like a computer do need to understand the word, the meaning of the words along some dimensions in order to do the inference better. So based on that, the next step other type of work we were trying to do is like if we already have representation for words, how we can combine the meaning of words to get the meaning of sentence. Again, so far people use transformers. There's many different ways to do this. So in principle, I just want to, probably you're already convinced, but I just also, if you're not yet, I'm going to try to convince you like the composition of the meaning is very complicated. For example, whenever you say, okay, this the feedback from this year's review is very positive, or it's not very positive. So this is not necessarily to be very contrasting, because very positive means very positive, but not very positive is probably not means very bad, right? So this is a negation. If a negation language is not a negation in logic, right? It's not totally reverse the meaning. For example, if it's very positive in sentiments, it's not necessary to be reversed to the very negative. So we do conduct some research on this to try to observe. We found like deep learning is very powerful to model this kind of compositionality situations. But there's more complicated situations, like if you want to build a question answering systems, if you want to build an inference system or natural inference system or sentiment analysis, computer need to understand composition. And if you build a QA system like a senator to formal senator, if you want to ask what formal senator can do, right? But formal senator do not have the same power as senator has. So that means if you put two concepts together, the composition is going to not just intersection. There's many much complicated semantics you need to model. So again, so the composition is quite complicated. Even now, I think most people are satisfied with use deep learning to like use transformer to get the meaning at the top and do some classification. But again, so I imagine for some more difficult task involved in reasoning and like a Winograd schema test, we need to design the model better to really make the models can understand the things over here. So so for that composition things, we actually developed some models for doing composition. One model we designed is based on the parsing trees. Because again, so many people do not believe parse trees because for many tasks like parsing trees actually do not help too much, which is understandable. For example, for sentiment analysis, the only things the most important things you need to know is the sentiment of words and the negation. But again, for many other tasks, especially many tasks is more sensitive to structures. I personally believe we need to build the model probably depend on some inductive bias, which can give him from the structure. So about 2 years or 3 years ago, we started building a composition model based on tree structures. So we do propose the tree RSTM at times which is published in ICML that year. So basically, we extended the linear RSTMs to the tree structures. Hopefully, we can can take the inductive bias from the given parsing trees. Again, so this is our starting point to start to combine the local the word meanings to the sentence meanings. So this is some details about RSTM. Now it's quite extensive, so we're not going to talk about that. But again, so the key ideas here is still there's some argument between how we should use the structure information. I guess this is also depends on your task. Like for some tasks, it's very sensitive to structures. Structures still very helpful. I'm going to talk about later. Some people use the tree RSTMs not to do language. They use tree RSTM to detect entailment in logic forms. In their task, I'm going to talk later. So in their task, the conclusion is if your task is if structure is central to your task, like if you are dealing with some logic forms, and if the structure you got have less noises, and then the models with the structure bias, it often works very good. So when I'm going to talk about that, some people use this to do to detect entailment in logic form. So again, for semantic composition side, we do have I just briefly mentioned, we do have a tutorial with Edward 2 years ago at ACO, which summarized by that time as a deep learning model for semantic composition. So I'm going to come back to inference again. So we start from modeling words, and then we talk about how to compose the meaning of words to the meaning of to get the meaning of a sentence. But one thing mentioned in the composition in this tutorial I didn't mention today is you remember a composition. Some words or phrases have good compositionality. You can learn from words to phrases, but some of them has less compositionality. For example, idiom a kick the bucket, right? So for kick the bucket, you cannot get the meaning of the phrase from the word. There's many other even trivial cases there's a whole communities working on multi-word expression things, but there's many trivial cases like a must try. If you said this is a restaurant you must try, then it's positive, a little bit positive. It's positive, but the positive cannot come from the word must and try. If you can't put the word must try together, you can model that. So we also build a model, but I'm not going to talk today. It's trying to get the meaning of the sentences by doing composition, but also give the possibilities. A model can not only compose from the low-level words or phrases, but also can consider the holistic information, whichever you can learn from other words. For example, if you from other words you know what the meaning of kick the bucket, you can incorporate that in the model. And also, if from other place you can learn the must try is positive, a little bit positive. You can incorporate those information. So we also build models to do semantic composition by consider both compositionality, or I would call it non-compositionality, or softly non-compositionalities within the model, building the inside the model. So that's for some tasks also help to solve the problem. So again, so this is the second task we try to do in the second problem. We try to, again, this is a very huge domain field to work on, but we try to solve some problem for the purpose of doing better natural language inference. So again, so we talk about two things right now. We have briefly about what if at the word level, we try to modeling the semantics along some dimensions like contrasting meaning, hypername side, use deep learning to model that. And once we get that, we'll also try to model the semantic composition by proposing some models which can compose the meanings or study the non-composition adding the meanings to get the meaning of the whole sentences. And specifically come back to natural language inference. We try to incorporate all these models to represent the inference. So this is a model we proposed at the beginning of 2017. So this model is quite, I mean, nowadays it's quite a standard baseline for natural language inference. It's called ESIM. So, the ESIM model we try to model because whenever you model the entailment or logical relationship between two sentences, you can consider you should grab the information, the local inference information, like the meaning of two words, the meaning of for example, like for the example I gave earlier, like you want to model like Toronto is part of Ontario. If anything about Toronto is true, probably it's something about this area is true because this area is part of Toronto. So you need to grab the local inference information. So in this model design, again, so we try to model the local inference information between words and the phrases. And then we compose a model to get the global information about the relationship between these two sentences. So I'm going to go to details a little bit about this model. Again, so the first layer we try to do to encode the in sentences, which is quite standard. I'm going to skip this. You can use a bi-RSTM, use tree RSTM to model this. You can also use transform-based models to model the meaning of each sentences. And then once you get the meaning of the sentence and each phrases, you can build attention models to detect the local inference information, like the relationship between a sum and any, between Toronto and Ontario. So this is local inference model is trying to grab the inference information between words and phrases. And once you get this, you can regard that composition. You can perform composition over local inferences to get the global inference information, which is we call inference composition or aggregation. So I'm going to go very quickly to each of them because nowadays people start to use BERT, but this is many of the ideas here is very similar to what you use to do the core sentence attention. So I'm going to skip this part because the layer one, the lower, the input encoding part, you can use many different ways to encode them. Like you can use a bi-RSTM tree structured. You're seeing it depends on the problem again. So if your input is not regular sentence, if it's a logical form, the research I'm going to mention later. So they use a tree RSTM actually get the best results. Then the local, the input encoding part, I skipped this because it's quite standard. And then we talk about the local inference model. Local inference, again, so once you get representation for each of these phrases or words, you can find the attentions, core sentence attentions to try to model the local inference information, local inferences. Again, so the key idea is like if I said that the two dogs are running through the field, and a hypothesis that there are animals running out dogs. You want to find the dog. You want to attend the dog towards the lion, right? You want to align them together. So this is a local inference. But again, so you also want to, whenever you read the computer read the word animal, they want to look at the word as well. So actually, it's do bidirectional. Whenever for each of the words, you want to attend one of those or multiple of them. Whenever you read this sentence, you also attend those again. So this idea is very similar to what BERT can do this because BERT put a sentence separate at the beginning, right? In the middle. So between the two sentences, they can model this as well. So, but again, so the ideas here is model the cross-sentence attentions to do for this. And one point that's very similar to quite significant in this field, like is whenever you model the cross-sentence attention, you should use these heuristics. It always helps the performance. Probably some of you already know this. So the idea is like when you have a word embedding for dog, or probably alpha I. So alpha I bar. So alpha I bar is a representation of a dog plus context. For example, alpha I can be a representation of this position from barrier scheme, right? And this embedding is like the context. It's a sum of this based on attention. So basically, again, this is the representation of dog in the context. This is a representation of the other sentence based on this word, right? So by manipulating these two vectors, you can some heuristic really help. So one heuristic will always help for this for cross-sentence representation, not only for NLI. It's like if you just minus these two vectors and also do the dot product of these vectors. For both of them, it's always help the performance. So this is quite standard like ways to deal with whenever people build the models. They always use this. So then we start to build the global. We try to build the model to make the global judgment. Again, the global judgment. Once you get the local inference information, you can run in any composition models. Like you can use the barrier scheme. You can also use a tree scheme. Use different models to combine the models. Again, so far the input is not word again. The input is not phrase again. Your input is like the local inference information. MA actually encode the relationship between the dog and the other sentences, right? So MA is a local inference information. So you put them in some models, you can get global information about the inference. So at that time, those kind of models actually. Again, so this model is called ESIM. Again, so at that time, so about 2 years ago, this model is a state of art. Nowadays, ESIM, whenever you deal with NLI, so ESIM is quite standard baseline you have to you compare with. Another standard baseline nowadays is BERT. So this is some work we did before. So we start to keep moving on to better model, try to better model the inferences. So there's two ways we try to better model inferences. One is we try to model these inferences if you are given some structures like parsing trees. I already talked about it a little bit before. Like even now, so not too many people between structures. We believe do not know how to use structure to help many tasks. But again, so language is not just a mere safe sequence. Language have structures. You have to either implicitly learn the structure, or you can. If sometimes you have this structure which is quite accurate, you can take advantage of it. Another is like external knowledge. If you want to do reasoning in some domain, like a financial domain, in the legal domain, so how you can incorporate external knowledge? Because external knowledge in financial domain, in the legal domains, maybe for your task in the system. So again, so we are going to talk about the further work. We try to improve the inference. Informal, we can explain what processing basically like a knowledge graph. The second type of is like a pre-train. You can always pre-train your model and doing the domain adaptation over your domain and add those information to your task. So I'm going to keep talking about more recent work on how to incorporate those two types of informations into the inference systems. So the first one is always you can take advantage of some structure. Again, it's dependent on whether how structure is the role of structure in your task. If your structure, I mean, when I said structure here, it means a syntactic structure, right? Whenever a structure is central to your problems, and if the structure you get is not very noisy, in many cases maybe can be helpful. So again, the structure can be used in different places in the inference system. The first thing you can use structure. You can encode the sentence and phrases based on the structure you already have, right? You can encode each sentence premise and hypothesis using some structures. You can also, once you get the local inference information, like MA and B, you can also use structure to do the aggregation. You can aggregate the local inference information to make the global judgment based on the structure as well. So here each node is one word, one phrases. Here each node is MA and B. It's already local inference information, right? So you can structure information for specific core inference task you can use use the structure in different places, encoding the input or do your aggregations over the structures to make global judgment. So structure information, we do say they have some good benefits. Like for some example, we observe like it do help you to align two sentences in a more ways to make sense way. And again, so we observing some examples like whenever you use structures can help you to have your attention to find the right time. Again, so really, I think I don't want to make an argument over here. So, but the things I argue here is like whenever you have a problem which is sensitive to structure, and the structure is less noise, and it can be helpful for your task as well. For example, again, if you deal with logic forms. So this is some experiments result I'm going to skip, but again, so if you use structure for SNI, you can improve the performance a bit by 0.6 a little bit. And we do some ablation task on some subset of the data set. We found the structure information can help a little bit. So this is the work I mentioned. Like some people try to use a tree model to detect whether this entails this or not, whether this entails this or not. And basically this is published last year, so it's not biased, this work. So again, so they try to, by doing this, they try to understand two questions. One is like, can neural network understand logic formulas well enough to detect entailment? The second is they want to find which tag texture are the best. So when they do this, remember recently there's a mini work about annotation bias or annotation artifacts. So whenever you build your model or your training set, if you're not careful about that, it's probably going to bring some annotation artifacts, which actually model is very easy to overfit towards. So when they build their data set, they do consider this to make them the model to less subject to those problems. So this is their result. I'm not going to if we skip this result for the time being. So the result, the conclusion, one conclusion they made several conclusions. One conclusion they made is like if the structure of an input is given unambiguous, and if the structure is central feature of your task model, that you probably need to explicitly explore those kind of structure. That means you probably want to build in some bias into your model, right? I think this is one observation they try to they conclude. I mean, even more recently, people apply deep learning models to do the theory proof. And if you can build in some bias into the model, for example, if you build like if you build some like a logic forms into your model, for some tasks they do help. So again, so I think this is the second task. The one direction we try to improve the model is like we incorporate the structure into the model to see why and how it helps and in what circumstance it may help the model. So the second direction we try to move, try to extend the natural language inference model is to incorporate external knowledge. So there's two types of external knowledge we can incorporate. The first type is like whenever you move to some specific domains, you have abundant knowledge about like some cases you have like a knowledge graph of some domains. And sometimes you have like a thesaurus of your domains, like which concept is a hypernym or a hypernym for that concept. So we try to incorporate this type of knowledge to help the model to understand the inference, natural language inference problems. So basically we have an external knowledge database, which is like a synonym or something shared in parents. So we have this kind of knowledge. We basically extract like a different semantic relationship in the word net, and try to incorporate this knowledge into the model. Again, so if you're dealing with your domain-specific problem, you can consider you have some domain-specific knowledge. But again, because of with the data we use is in general domain, so we just try to incorporate general external knowledge from general domain, like from word net, from concept net.
So basically, there's several ways we try to incorporate the external knowledges. One is like external knowledge is going to help us to do better attention. For example, if you mention like Halifax, the price in Halifax, the house price in Halifax increase. If you set the house price in Nova Scotia increase. So if people come from other country do not know the relationship between the Halifax and Nova Scotia, so they probably don't know the relationship, right? So if you train a computer who do not know the domain knowledge, they probably cannot make a judgment. So that's the intuitions like we want to incorporate those external knowledge which is not presented in training data to the model. So one way is they're going to help us do attention. If we know the relationship between, if we said the house price in Halifax increase or house price in Nova Scotia increase, the computer, the relationship between Nova Scotia and Halifax is going to help us to find the alignment. So attention is going to help us build a better attention model. So one way we incorporate external knowledge to help attention itself. So we incorporate this is external logic between the word I and the word J, or phrase I and phrase J. You can incorporate this into an attention model. So it's quite straightforward. We also incorporate them whenever you calculate the relationship of the local inference. You can always incorporate external knowledge over there. There's different ways to incorporate them into your local inference information. So this is a result if we test on SMI. So it's improved the performance a little bit. Again, so it depends on your task. But the same year when we published this in last year's ECO 2018, so there's another group of people from Israel. So they actually built another data set which tried to, they built another data set, we call it graph data set. In that data set where our performance actually is much more impressive. Again, so I just briefly introduced their data set. So their data set basically say, I'm going to observe whether a machine really learned the inference or not. So they build a data set just by build some example that change one or two words and make sure these two are counterfactual, right? South Korea or North Korea. And try to test use this, you can basically think about it as a type of adversarial examples. So they use this to test all the previous models. So all the previous model is only based on the training set. So their performance in SNI, the first three models, previous model, their performance in previous data set, SNI, the three model in SNI, again, SNI is a standard MLI data set. This is a new data set, a smaller data set. So the previous three models performance are very good in this SNI. But the performance dropped dramatically in this newly built model. For example, this model dropped from 80 to 60 or 50. But whenever you incorporate external knowledge, it's going to be very consistent on this kind of test. Again, so if you think about you are going to build a model for some specific domain, that basically means you should definitely use a domain knowledge to retrain your models to enhance your model in this way. So, so this is one way to enhance to get the external knowledge from some structured data you already have for your domain, or in general from general domain, like for example for word net or concept net. Another way to incorporate external knowledge is use BERT, right? BERT, you can think about BERT can learn many different things. But one thing BERT can learn is learn the semantics. BERT can learn many very interesting semantics. So we do some analysis work on BERT to how BERT can learn some things. So BERT can learn like sunlight, moonlight. So BERT can learn these two things are contradictional. So they can learn very well these two things are contradictional. But again, these two words are not in WordNet. So if you incorporate the knowledge from WordNet, you're going to miss this information. But if you use BERT, they can recover this. So that means BERT and the KIM, the model we proposed in BERT, they actually can complement each other. Like sometimes BERT can learn things better. Sometimes the KIM can learn things better. So we do some analysis from these situations, like basically BERT can learn external knowledge from pre-trained data. And KIM actually can leverage information from human annotated like data and corpus. So again, based on this, we propose more models to bridge them together, to bring them together. So this is a model we just, one of my students doing is to incorporate structured knowledge with pre-trained model. Basically, you can think about pre-trained model is going to leverage on structured data. And if you have some way to leverage structured data, like concept net or word net, you can probably build a better models for natural inference and some other tasks. So one of my students is trying to incorporate the structured knowledge into pre-trained model in different layers of problems, in attention layers, in different layers. And also, one of my other students is trying to doing research on adaptation, domain adaptation for pre-trained model. So this is so this is the bird from different layers of original translation block. They have 6 layers of bird have 12 layers. They try to incorporate this knowledge in different layers to see how structured knowledge affect different layers of the model. For example, lower layers and higher layers. Higher layers is more like a more abstract semantics syntax. The lower layers is more close to word level. So they try to incorporate the structured knowledge and try to find how the structured knowledge can affect the birds, can be merged with the knowledge learned from birds. So again, the idea is very similar to the previous models we built. It's like we incorporate structured knowledge to the VKQ to the attention part, and also to the local inference part. We also incorporate the external knowledge. So EIJ is external knowledge to different components of the model. So basically, these are some details. Basically, we found we can consistently improve the performances. Like this is ESIM Kim. So ESIM is our the baseline model. Kim is from 2018 ACO. So when people propose element, they also use our ESIM as a baseline to add element over the ESIM we propose, right? And then GPT and bird base, and then we try to incorporate concept net and towards the word net to the model. And for different data set, like SNI is one natural language inference data set, and the multi-NI, and also the long-term data set, we saw some improvement over the model if you incorporate like a structured information over the structured knowledge you learn from use a pre-trained model. So again, so far we talk about one problem is like a natural language inference problem. But inference in language can involve other problems. Like one problem is Winograd schema challenge. So Winograd schema challenge, how many of you know the Winograd? Yeah. So Winograd schema challenge is a problem proposed by Professor in University of Toronto, Hector Levick. So he basically proposed like I guess some of you already know that. Just very briefly describe that. So basically, if you are giving computers given sentence, John cannot lift his son because he's too weak. So who is too weak? John cannot lift his son because too heavy. Who is too heavy? So this is super easy for human beings, but it seems to be super hard for computers. Because to understand or answer these questions, you need common sense. So from years ago, so like from the beginning, the first challenge is actually having EJIC at 2016 in New York City. So we collaborated to try to solve these problems. That time's Chen Liu is a visiting student in York University. So we collaborated with Professor Hui Zhang to try to solve this problem. So they proposed a model which only barely better than random guess. So random guess is roughly 50%. If you guess this, so who is John cannot lift his son because he's too heavy. Who is too heavy? John is too heavy or his son is too heavy. So only if you random guess one of them is roughly 50%. And then we tried the best model that time is roughly 60%. And now if you use BERT, another visiting student, he use BERT plus some housing tree information can push the performance to roughly 72% right now. So we do work on Winograd schema challenge right now. We try to also to try to solve different attack different type of inference problems in language. Again, the second problem we are interested in right now is we are going to host a competition in Semivale 2020. So the task 5 2020, we are going to ask the participant to detect a counterfactor. So the counterfactor is like this. So the first expression sentence is like if the US and China has reached an agreement in May, the stock price of Apple would have been much higher. So basically, the task is trying to, we have two subtasks. The first subtask is trying to classify whether a sentence mentions some counterfactor information or not. Counterfactors basically means against the facts. And some people, again, argue this is very important. Like Judy Per write a whole book about it. Like he argued like this kind of counterfactual reasoning is very important. That's top rank of the layer of causality. So if you think about it, I usually imagine like if I didn't come to University of Toronto 13, 15 years ago, then what's going to happen? So we use this kind of as information to help us make decisions, right? And some of them argue this is very important also for evolution of human beings. But again, so if we do not talk about that, the task here we design is to first subtask is to detect whether this sentence mentioned a counterfactor or not. So another example in medical domain is post-traumatic stress could have been avoided if a combination of this and this therapies had been prescribed 2 months earlier. So the first task we want to detect this. The second task we want to detect the reason and also the consequence. So we design this task. We want to model the counterfactual detection here. The key one motivation we want to do this is like before we talk about entailment. But entailment, you have different type of entailment, and the causality is one of them. But we think it's a very important one. So that's why we are trying to also model causalities in natural language. So this is the two other problems we try to solve. We try to understand more. Again, so today I talk about three types of natural language inference tasks. Three types. The first is natural language inference itself. The second is like a Winograd schema challenge. I probably don't have time to talk about this in detail. And third, it's a counterfactual detection. So those are three problems we try to understand it better in my lab. Is try to model this. The reason again is we believe like modeling semantics and also this reasoning is key to many tasks. I just use one slide to talk about what we are doing there in my lab. So we basically think about the semantic representation reasoning. It's very important. And based on that, we have several applications we are also have some students working on. One is like we have a project with a professor in the law school in Queens. We actually get this is called a new frontier in research in Canada from some government agent from Canada. So we try to apply semantic representation, composition, and reasoning to analyze the legal document because there's a lot of reasoning over there. And one of my students should try to apply this for financial data analytics because I have a previous master student have a company in Beijing. He's trying to do some like he use financial data to predict stock price. So he's a company with roughly 100 employees right now, but he has not started to use a natural language yet. And they won't mainly use financial reports, those kind of data to predict the stock price. Seems like I don't know the details to that, but seems last of the summer I visited them. Seems the returns quite good so far. And also I'm not working on this, but I put one student to work to try to understand the financial implication of using the model some of the model we built. And again, so if you consider today, like whenever Donald Trump put a tweet online, it's going to affect the market right away. So in the US, it's within like a couple of seconds. And in China, within 1 minute, the market is going to respond to that. So those decisions cannot made by human beings. It's made by automatically. So I started put one student working on this, and I also have some collaborations too with other places. We try to do some QAs. And also before when I did my master in PhD in University of Toronto, my thesis is about summarization. So I still have some students start working on summarization. So again, I should not talk too much about this again. But again, so my lab is going to have some. We hope we can do some research on doing to understand better how to represent the meaning. But again, so that's a huge problem. And how to do some reasoning and inference in language. And we are also look at some applications we can apply the model we have already built. One thing we do, I didn't mention here, is also sentiment analysis. We did that for years as well. So this is basically my talk, and I think I want to thank you everyone for your time to hear. So, and do you have any questions?